Welcome, class. So in the last video, I stopped on, I gave you this problem right here. And I drew a resonance structure, and I asked you to tell me if it was legit or not. Can we do that? Versus this guy right here, the same molecule as above, but this time taking that double bond right here and moving the 2 pi electrons there. So let's take this top one and draw exactly what the arrows are telling us to do. We have 1, 2, 3, 4, 5 bonds, or 5 carbons. And I said we're going to move that double bond over here. But before we do that, how many hydrogens do I have on this carbon? I have 1 hydrogen, so I have to still have 1 hydrogen over there. The atoms don't move, it's only electrons. How many hydrogens do I have on the carbocation? Just 1. Right. Now we bring that double bond over, boom. Now we reevaluate. What's the formal charge on this carbon? It was positive over here, but where is it? What is it now? And we can see that there's 4 bonds, so that's going to be neutral. This carbon right here that I'm pointing to, that one has 4 bonds, but now how many bonds does it have? Only has 3. So that would make that carbon right there a positive charge. And this is a legit resonance structure because we're not breaking any of the rules that we've been taught up to this point. Do we have any Texas carbons? Nope. So that's good. Now, if we take a look at this second structure right here, let's just draw what the arrows are telling us to do. We have a carbocation there. It's still there. This double bond moves over here. And then now we have to reassess the formal charges, right? So how many hydrogens are on this carbon? 1, 1. And how many are in this carbon? There's going to be 3 of them. So now we reevaluate. We still have the hydrogen there. There should still be 3 hydrogens there. If we take a look at this guy, how many bonds does that carbon have? Only 3, so that would have to be a positive 1 charge. And whenever you have a positive and a positive right next to each other, it's really, really high in energy and unstable. But why is this resonance structure, or should I more accurately say, this is not a resonance structure? Because this does not exist. Why? Because we have a Texas carbon. You can't have 5 bonds. So the pi electrons here cannot move in between these 2 carbons because you would form Texas carbons. So this is a valid resonance structure right here. And this one below is not, cannot happen. Okay, so let's take a look and build off of this concept of resonance structures. What you're going to be able to do is you're going to have some resonance structures here, or yes, resonance structures. Making sure I'm not getting cut off on the slide there. Okay, so we have something like that. And we'll draw a resonance structure for it. And then draw ourselves a third one. And I'm going to label these 3 resonance structures. Remember, it's 1 molecule. These are not three separate molecules. It's just one molecule with three resonance structures. So I'll label that one A, that one B, and that one C. Now what we can do is we can look at these three resonance structures and we can assign which one is dominant. So when you have three resonance structures, which of these three resonance structures does the molecule prefer to look like? And so what you have is significant resonance structures, somewhat significant, insignificant resonance structures. And so basically, you can rank them. Which one, what's the word? I'm blanking for a second here. Which resonance structures, which one of these three contributes to the resonant hybrid the most? So in order to look at these three resonance structures, they are all valid resonance structures, but which one contributes to the resonance hybrid the most? And in order to know how to answer that question, you need to understand some more principles. And so the first principle that you need to know and be aware of is this. And I'm going to read it to you. So write down this sentence. The most significant resonance forms have the greatest number of filled octets. Let me read it to you one more time. The most significant resonant forms have the greatest number of filled octets. So what does that mean? Let's look at an example. Okay, so let's look at an ether. All right, so we have an ether here, like so. And then we can draw a resonance structure for this guy. And the way we could do that is we could take this lone pair right here and just bring it in between the oxygen and the carbon. And so that's going to make us have a resonance structure that looks like this. Double bond to the C, CH3H, right? Now this is rule one. Which resonance structure between these two is the most significant? Now let's read the rule again. The most significant resonance forms have the greatest number of filled octets. So if we take a look at our oxygen here, you can count and see that it has 8 electrons around it. Its octet is filled. But this carbocation only has 6. When you compare and look over here, what am I missing over here? So you see how it's positive charge over here and it's drawn as neutral right now? So that's like a trigger in my mind, like I've done something wrong. Positive, that still has to be positive. Well, the oxygen right here has 3 bonds to it, so that's going to be +1. But when we take a look at the oxygen, it still has 8 electrons around it. And then we take a look at this carbon, what happens? It has now 8 electrons around it. So comparing these two resonance structures, we would say this one over here is the major contributor, and this is the minor because of that first rule. All the atoms in this molecule, or this resonance form, sorry, has an octet. This one, that carbon right there, does not. So when you compare the two, this one wins. Now, I'm going to teach you 4 principles. This is the first one. Now, these principles, they're ranked in high order and ranked in prevalence. So whenever you look at resonance structures, you start with rule 1. And then the second rule is next, and third and fourth. Okay? So let's take a look at rule number 2. So let's erase this. So rule number 2. Okay? And rule number 2 is the structure with fewer formal charges is the most significant. So if we take and look at a molecule that looks like this, and then that's going to have a resonance structure like this. And H2, negative charged. And then that would be positive. Now let's make sure we see where the resonance structure are coming from. So this lone pair is going to come down and then kick. So those pink arrows are going to give us this one. And then we can say, hey, we could take that, put it back, and it would give us that one. So we have three resonance structures here. Now which one is going to be the most significant? Now when we take a look at now we have three, okay? So first off, we have to apply rule 1. What does rule 1 say? The resonance structures that have full octets are going to contribute the most. So when I look, this nitrogen has an octet, that carbon has an octet, that nitrogen has an octet. So I'm thinking in my mind, okay, that one has an octet, all the atoms. This one, let's see, this carbon has an octet, that nitrogen has an octet, and so does that one. So that one all has an octet. But then we take a look at this one. This carbon does not have an octet. So based off of rule number 1, when we look at these three, we can say, hey, this one is the least. It contributes to the resonance hybrid the least because of rule 1. Now, rule 2 states the structure with fewer formal charges is going to be the more significant one. So I'm looking at these two right here. I see that this resonance form has 2 formal charges. This one has none. So that makes this one the most significant. So if we had to rank these from most to least, that would be number 1, 2, and 3. All right. So rule number 2, you're just looking at the formal charges, but you cannot skip rule 1. You have to look at rule 1 first, then rule 2, and now we will go to rule 3. Let's see here. Yes, let's jump to rule 3 now. Okay, rule number 3 states, all things being equal, a structure with a negative charge on the more electronegative element will be more significant. Okay, so rule 1, everything has an octet. Everything has an octet. Good, so we cannot distinguish between these two, which one contributes to the resonance hybrid the most. Based off of rule 1, there's a tie. They all have octets. Okay, rule number 2, the amount of formal charges. Has 1 formal charge, has 1 formal charge. Tie. Rule 3 is going to help us break that tie. And rule 3 states, once again, all things being equal, a structure with a negative charge on the more electronegative element will be more significant. So what do we have here? A negative charge on an oxygen, a formal charge on a negative on an oxygen, and a -1 formal charge on a carbon. When we look at the periodic table, what is it? We have carbon, nitrogen, oxygen, fluorine, right? Which one's the more electronegative? It goes in that trend. So oxygen is more electronegative than carbon. So a more electronegative atom is going to tolerate and be okay with a negative charge, whereas a less electronegative atom, such as carbon, isn't going to tolerate that negative charge as well. And so what we have is this form is going to be higher in energy, more unstable, and less likely because the molecules want to get lower in energy and more stable and more happy. And so a negative charge on a more electronegative atom is going to be lower in energy, more significant, and just overall better. So this one is more significant because of that third rule. Okay. Now you can take that principle and apply it to positive charges as well. So if we take something that looks like this, let's draw ourselves an amide. Amide like this. And what we actually have is a protonated amide. And one thing I did not do for this one above here, can you see the arrow movement or the electron movement with the arrows? I'm going to take this lone pair and bring it down like that and go like that. So those are the arrows that get us here. So I now want to take this lone pair, bring it there, and put the electrons back onto the oxygen like so. So what do I have now? Positive charge. Like so. Okay. Now, if we go through rule 1, tie. Rule 2, tie. Rule 3, which one is going to be the major contributor? Well, now look what we have going for us. We have positive charges, okay? And now we're comparing the formal charges on an oxygen and a nitrogen. So these two. So when you look at nitrogen and oxygen, we know oxygen is going to be more electronegative. And because it's more electronegative, it's going to hurt more when it has a formal charge of +1. Because oxygen wants to have a negative formal charge or can tolerate that better and because it's more electronegative, but now it's positive, and that's just like, ugh, hurts. But nitrogen, on the other hand, you can see is less electronegative. So it can tolerate a positive charge better. So when you're looking at these two resonance forms, you've gone through rule 1 and rule 2, now you're at rule 3, and you'll say this one is going to contribute to the resonance hybrid the most. So this is the more significant resonance form due to rule 3. All right. We also have a fourth rule. The fourth rule here states resonance forms that have equally good Lewis structures are described as equivalent and contribute equally to the resonance hybrid. So let's take a look at carbonate. So that's CO3 minus, 2 minus, like that. What are some Lewis structures here for this guy? Negative, negative, okay? Now we can draw some resonance structures. I could take, let's do a different color. Could take this lone pair, move it there, and go like that. So what would our new resonance form look like? So that's now negative, that's still negative. And we could draw a third resonance structure. And what could we do now? We could let's see here. We already did that one. So we could go like this. And then kick those back like so. So now we're going to have negative, neutral, and negative right there. Now, rule 4 is telling us that when you take a look at every single one of these resonance structures right here, each one of them is going to be equivalent. They're the same. Go through rule 1. Everything has its octet. Check. Everything's a tie. Rule 2. Fewest formal charges. Well, they all have 2 formal charges. Okay. So rule 3. The formal charges are all on oxygen. So you can't break a tie, right? So rules 1, tie. Rule 2, tie. Rule 3, tie. So rule 4 is just saying, hey, when that happens and everything's equal, then these resonance structures, these 3, are all equivalent. Okay? They contribute to the resonant hybrid equally. Right? So now that we have learned the principles now behind looking at resonance structures and determining which one contributes to the resonance hybrid the most, we can now tackle this problem up here. So it's always a good idea to be able to see where the electrons are moving. So to go from A to B, I'm just taking those electrons and moving it there. Now, going from B to C, what do we have to do next? It looks like we're going to bring in a lone pair on the oxygen, like so. Okay? So now we have our 3 resonance structures. Now let's rank them. Now, how do I want to rank them? So on tests and quizzes, you have to look at the question very carefully. Let's see. Rank the following resonance forms from most significant to least significant. Okay. So what is rule number 1? Got to go down in order. Rule 1. The most significant resonance forms have the greatest number of filled octets. So let's take a look here. So C, everything has a filled octet. Okay. B, every element has a filled octet except for the carbon. So no filled octet. So I'm just making myself a note. And then when I look at this, okay, that has the octet, everything has an octet. So right out of the gate, I can tell you that B is the least. It contributes to the hybrid the least. Least significant right there. So now we have to break the tie between A and C. And so what's rule 2 state? Looking at formal charges. This form has 2 resonance structures, or 2 formal charges. This one has 0. So that makes this one the best. So if we rank these, this would be 1, 2, and 3. And once you have them ranked, you don't need to keep going down the list of the rules that I taught you. You just start at 1, go to 2, and in this particular case, we did not need to talk about rule number 3. And so we would rank it like this. C is greater than A, and A is greater than B. Okay. So that's how you tackle problems like this, using those rules. So you have to get them in your head, know their ranking, and use them in the proper order. Okay. Next thing that we want to talk about is hybridization. So hybridization here is a concept that you've learned in general chemistry, and we need it now. So let's take a look at a tetrahedral carbon. Okay. Like this. And let's expand out these hydrogens here. Okay. So when I look at a molecule, how do I know its hybridization state? So if I want to know the hybridization state of that carbon right there, well, all I do, okay, is I look at how many bonds are directly attached to that carbon. And I see that there's 1, 2, 3, 4. So there's four bonds to that carbon. So that's going to make it a sp3. If I have a carbon that looks like this, an alkene right here, what is the hybridization state of that carbon? I count how many electron groups. That's a better way of saying it, class. So let's backtrack to this one. How many electron groups are there? There's 1, 2, 3, 4. So 4 electron groups, sp3 hybridized. Now in an alkene, how many electron groups? There's 1, 2, 3. We count the double bonds as 1 electron group. And so there's 3 electron groups around that carbon. That's going to be sp2 hybridized. And then if we have a alkyne, and I take a look at this carbon, how many electron groups are around that carbon? 1, 2. So that would make that a sp hybridized carbon. That is an sp hybridized carbon. That one is an sp hybridized carbon. But what is the hybridization state of that carbon? There's 4 electron groups around it, so that would make it sp3. Okay. So let's take a look at let's go like this. So now we have an anion. What is the hybridization state of this anion? Well, we're counting electron groups. Right? A lone pair is 1 group, 1, 2, 3, 4. So that would be sp3. Okay? So if we had an ether, and I just drew the ether like this, and I asked you, what is the hybridization state of the oxygen in that ether? Be honest with yourselves. How many people would say sp? Because there's 1 electron group, 2 electron group. Gotta be very careful because that oxygen has 2 lone pairs that may not be shown, but you should already know that they're there. So when we take a look at this ether, we have 1 electron group, 2, 3, 4. So that ether is an sp3 hybridized. Now, well, it may be a challenge, but you learned how to do this in general chemistry where you look at Lewis structures and everything's all spelled out for you. But we are in organic chemistry now, and so you have to be able to look at skeletal structures like this. And we could go like this. Okay. We can just make the molecule look in all different ways here, okay? What is the hybridization states of the indicated carbons? I could say, what's the hybridization state of that carbon? And you should draw in all the hydrogens. So that carbon right there has 3 electron groups, so that carbon would be a sp2. What about this carbon right there, or that one? Both of those would be an sp, because it has 2 electron groups. So let's take a look at this terminal alkyne. Well, there's a carbon there. Let's draw it in if we want, and then that has a hydrogen. So this carbon right here has 1 electron group, and then it is bonded to this carbon right here by the triple bond. So 1, 2. So that's the sp. What about this carbon right there? Well, that carbon has a electron group there and an electron group there. So there's 2 electron groups, but please do not forget the hydrogens. So that's 4 electron groups, so that's sp3. All right. And carbocations right there. How many electron groups are there? Well, we got to remember that there is a hydrogen coming off of there. So this carbon right there has 1, 2, 3 electron groups, so that makes that sp2 hybridized. Okay. Now that right there should be the review. But so the very first part of it was review. This is putting in the skeletal structure. So now we're mingling in our organic chemistry. Now we have to take a look at molecules that have electrons that are localized versus delocalized. So if I have a amine like this, okay, what is the hybridization state of that nitrogen atom? Well, you look at it, there's an electron group there, the lone pair 2, 3, 4. So that nitrogen is in fact sp3 hybridized because it has 4 groups. Now, what if I had an amide? What if I draw an amide that looks like this? What is the hybridization state of the nitrogen atom? Well, you'll see 1, 2, 3, 4. So you say that it's sp3 hybridized, but it's not. You have to be very careful here. That lone pair can resonate in. There's already those. So when that lone pair resonates in, I'm going to draw it down here. So I ran out of space. All right. How many electron groups are around that nitrogen? 1, 2, 3. So now that nitrogen looks like it's sp2. So is it sp3 or sp2? The answer is the nitrogen is sp2. This nitrogen right here is not sp3. It is still sp2, even though it looks like it's sp3. And it's not sp3 hybridized because the lone pair can resonate in. And so the difference that we have here is that this lone pair right there is localized. It cannot resonate into that carbon like that, because then you would form a Texas carbon. That does not work. So because this lone pair right here can't move via resonance, it is localized. And since it's localized, it's going to be sp3. This nitrogen, on the other hand, the lone pair is delocalized because it can move around via resonance. And so when that happens, you can take and look at both resonance forms, and You just find the one that has the smallest amount of electron groups. So here it has 4 electron groups, here it has 3. So you go with the lowest number. And so that makes that nitrogen here sp2, this nitrogen here sp2. So you can apply the same concept now to the oxygen. How many electron groups are around this oxygen? There's 1 lone pair, 2 lone pair, double bond. So 3 groups. You might think you would say that would be sp2, right? Because there's 3 groups around it. But then when you take a look at this oxygen, how many groups are around it? 1, 2, 3, 4. And you might say it is sp3. But it's not sp3. Both oxygen atoms are sp2 hybridized. Right? The lowest of the 2 is the one what it really is. Another way, or the way the textbook is used describing this, is if the electrons are localized versus delocalized. Do you see how this lone pair right here is delocalized because it's there in this resonance form, but it's not there in this one? Where is it? Is that lone pair right there has become the double bond in that carbon oxygen right there. It's become the carbonyl carbon, or the carbonyl bond. Okay. So the moral of the story, when you see a structure, you have to establish if the lone pairs are localized or delocalized. Okay. So really stare at that. Localized, delocalized. Okay. So you will be given on quizzes and exams a very complex looking organic molecule, and I'm going to draw arrows to certain elements in that molecule and ask you to tell me what the hybridization state is. You could also just sum this principle up. So this is a principle, okay? Localized versus delocalized. You can also just make a statement that the amide nitrogen and the amide oxygen right here, they're going to be sp2 hybridized. All right. So we could draw ourselves a molecule that looks like this. Okay, so there's an amide, right? Well, we've got to draw another hydrogen there. But I could tack on an amine. So this right here is sp2. That is sp2 because the lone pairs are delocalized, whereas this one is sp3 because that lone pair cannot resonate in. Right? Important principle. And one reason why this is so important is because you're going to see it over and over again in Orgo 2, and you're going to see it in biochemistry. Hybridization states is very important to help us understand reactivity and why molecules do the things that they do. So let me just overstate it. Hybridization states helps you to understand chemical reactivity. And that's what's coming. So if you can't identify hybridization states, it's going to be really hard to predict reactivity, and then you're just going to fall further and further behind. So if this is confusing, please reach out to someone, myself, TAs, and get the help that you need. So let me just take a look at my notes to make sure I'm not missing anything. And I don't believe I am. So what I will leave you with is it would be a really, really good idea to do these problem sets right here. These are called the conceptual checkpoints. Problems. And the ones that I feel are important for you to know is problem 18 and 25. Now, of course, there's going to be more problems in your textbook, which I'd highly recommend you to do, but at a bare minimum, and in this class, a bare minimum gets you a D or a C. That's what you have to do. But there's going to be plenty of problem sets in the textbook and on the extra credit that will get you what you need. Okay? So as always, please reach out if you need anything. I'm here to help.